So let's go ahead and graph these three things. And we'll be able to relate to transformations that you've done before, where you transform the graph of a quadratic function, aka a parabola. So the first one we'll do is the graph of f of x, which is x squared. So we have a point 0, 0. We have a point 1, 1. We have the points 2, 4, right? And then always is a reflection. So we are putting this as parabola. Real quick, seems like there's something suspicious going on with the graphs of g of x and h of x. Let's look at g of x. Well, isn't that 2 squared times x squared plus 1? Alright, so that is the same thing as 4x squared plus 1. Oh, which is the same thing as h of x, right? So let's not graph the same thing twice. Yes, it is a t. Alright, so when x is 0, y is 1, right? When x is 1, y is 5, right? Just going through a table of values. Why don't we do that real quick? I'll just go ahead and draw the table for x and g of x is the same thing as h of x. But we'll put g of x. So at 0, we're at 1. At 1, we're at 5. At 2, we are going to be at what? 4 times 4, 8, 9. So, and each one of these is a reflection, right? Since it's a parabola. I will get very different things. All right. So, what happened? What happened? What was the sequence of transformations to go from f of x to h of x? Well, it looked like this was a auxiliary. This was a vertical translation. Of positive 1, right? What happened here? Some people call it a shrinking or compression, right? Let's call that a horizontal scaling, right? Horizontal scaling, I think that's a more precise way to talk. Rather than saying compress or stretch or what's the other one? Squeeze. Let's call this horizontal scaling. And what's the factor? It's a factor of 4. We already did that. Actually, we should point to that. Rather, we did that because I can't stand when you can use some sort of property, simplify something. I have to simplify it. And so we did that. All right. Hey, you know what some good news is? I'm not doing that. I know I said the P word. Park. Hey, we're not going to do this. That's why I made sure to let you know what I'm talking about. Not doing that as well. Let's move right along to logarithms. Okay, so we've got the function f of x equals log base 2 of x. We're going to plug some numbers in there and get a handy dandy fancy table. All right, hey, when x equals 1, right? 2 to what power is 1? Right? I'm plugging all these values in there. Log base 2 of 2 is the same thing as saying 2 to what power is 2? 1. Log base 2 of 4, right? Plugging this in. Log base 2 of 4. 2 to what power is 4? 2, so then this must be 3 as well, right? Let's go ahead and graph those. Okay, so 1, 4, negative 2. It's gonna be weird. It's gonna be like real close, right? And then negative 1, 1/2. I'm sorry, 1/2 negative 1. I don't know, something like there, maybe. And then 1, 0 is right there. And then we have 2, 1, 4, 2, and 8, 3. Hey, let's go ahead and take it out to 16. Wouldn't that go right there? It sure would. And then again, right, this thing has this asymptotic behavior here. And it looks like that right now. Yeah. An asymptote, right? It's that's when your function has been friend zoned.
It's like second generation. She was like,
I wish our kids were best friends.
no, I wish our kids would get married. Hey, that's cool.
How about that one? Oh my god. Like, not dog so stuff.
Okay. Let's describe the sequence of transformations that takes the graph of f, which was log base 2 of x, onto the graph of log base 2 of 8x. Now again, I see that I could use a property of logarithms in here, and I have to. I can't stand it, right? I have a product inside of my parentheses, which means that I should probably take and make log base 2 of x and plus log base 2 of x. Oh, sorry, it's 8 and x. I said the reverse of what I wrote. What's log base 2 of 8? 3. Yeah. So what do you think the transformation is going to look like? And obviously this is the same as h of x. Right? That h of x right there. I know. Your ego's trying to get tricky, but
You believe?
yeah, you could say that. Okay, so what's going to be the sequence of transformations? Well, there's just going to be one thing that's going to happen. What does this 3 do? Just like with the graph of x squared, that parabola, right? If I do x squared plus 2, it's going to shift that parabola up 2, right? Same thing with the logarithm. If I have a 3 out there, that's going to be a vertical translation of positive 3. So, we have already determined that g of x and h of x are the same, so let's not do the same thing twice. This turned out to be -2, -1, 0. Log base 2 of 2 is 1, 2, 3. Alright. Right, just, we already completed that table, so that's why I went so quickly. It's over there on the other page right there. So, but for g of x, we have none. What's going to happen? If we're adding 3 at the end, right, isn't that going to be the same as just adding 3 to each of our y values? Yeah? I'm going to show you why that's true when we graph it in the next step. So then, if I'm adding 3 at the end, then it looks like this is going to be 1, 2, 3, 4. See all these weird patterns. Right? I'm like not even having to think. Oh, that's weird. 5 is adding, so let's go ahead and graph these. And I can do it without my table. So first of all, we're going to graph f of x, which you've already done. It looks a lot like, let's see. Right, it looks like that. We've graphed this a couple times now. We graphed it in lesson 17. We've graphed it just recently. So it should get to be kind of second nature. But now let's graph the next one. And remember, we said that it was a shift of 3, right? That's a vertical translation of positive 3. So that means that if I want to graph that one, all I got to do is go to each one of my y coordinates, right? Go to the point and shift the y up 3, right? Which is the same as what I was doing over here in my table. I was just adding 3. So let's do that. Let's add 3 to each of our y coordinates. 2, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. You guys don't have counteractive on your line. 1, 2, 3. 1, 2, 3. Hey. If you wanted to check that out, You could go to your handy dandy graphing calculator. Let's check it. So right here we have f of x, and this one is g of x, which is the same thing as h of x. Did you see how I did that? I did that transformation by just adding 3 to each of my y coordinates, right? And I don't know, it should make it kind of obvious why then. If I add a 3 at the end of the logarithm, right? If I take any log, log plus 1, log plus 3, on the outside of my logarithm, it's going to be a vertical translation. Fantastic. Let's move right along. We already did this, because I couldn't stand it. Remember at the beginning to say that, yeah, I couldn't stand that there was a property that could be done. So we did that. How about this one? The graph of p of x, log base 2 of 1/4 as a vertical translation. Well, again, I see that there is a property of logs that I can use here, right? I could subtract them. So it is true that log base 2 of x over 4 is equal to log base 2 of x minus log base 2 of 4. 2 to what power is 4? Alright. If having a plus 3 at the end of my function, I guess, was a vertical translation of 3 units, then this must be a vertical translation of -2 units, right? -2. Hey, this is actually not an okay thing. The answer to that is it's not. It's not. You can make it look like it, but it's not. And I don't like it. So I'm not. It's like almost like a way to compare. Okay. Moving right along. Now, are these the same? Let's go ahead and justify our reasoning using technology. First of all, I just cannot stand that this is 3 plus log base 2 of x, right? I don't like that. 2 to what power is 8? 3. So let's make it a 3. Let's go ahead and go to our handy-dandy graphing calculator. Oh, except for, not all of you have the log base function. You'd love this to be in log base 10, wouldn't you? Yes, you would. So if I make this log base 10, that's going to be log base 10 of x over log base 10 of 2. And then for k of x, I'm going to write that as log base 10 of what's inside my parentheses, so that's x plus 8, divided by log base 10 of 2. And now I can graph those with any calculator because I'm fancy. Okay. So let's do it. 3 plus, not divided. So there is, what did we name that thing? We named it h of x, and now let's do k of x. Do you need to see that again? Sorry, I moved a little quickly. Do you want me to go back to y equals? Okay, so the blue is h of x, the red is k of x. What happened?
The 8.
Yeah, that's right, dude.
Unless the other one.
Sorry, bro.
That's black.
That's red, bro.
No, bro. So it looks like if we describe how we got from blue to red, right? From h of x to k of x. Looks like it shifted down 3 units, right? And then to the left, I know, I have to do things backwards when I do it. To the left, 8 units, right? So let's talk about what happened, okay? Because we have a plus 0 here now, right? It shifted it back, right? So if we are transforming from, if we're going this direction, right? From h of x to k of x. This put us back, right? This shifted I don't want to write it like that. Anyhow, because there's a 0 there, right? It shifts it back. But let's look at this. What did this do? This is a shift. Let's not call it a shift. I want to stick with the same terminology. We're going to call this a horizontal translation. Translation. We're going to go -8, right? Even though it says +8, it's going to be the opposite. It's going to be -8. And that's really the new information that we got out of that. Okay. Hey.
Be right that you're not saying because that one has a vertical translation of 3. Never right.
Yeah. But also you gotta look at that horizontal translation.
So you have to look at both of them.
It was transformed twice. Alright. Hey! Let's talk about why these things are identical. Well, if f of x is equal to 4 to the x power, isn't that the same thing as 2 times 2 to the x power, which if we use our properties of exponents is 2 to the 2x. Is this printer? Oh. That's true too.
She did. But she goes
Okay. Ready? Alright, let's use properties of exponents to predict what the graphs of g of x and h of x are going to look like. Well, let's look at g of x. Let's do some interesting math to this. Isn't that the same thing as 2 squared times 2 to the x? Let me write the first step. I'm sorry. That is my next step. I'm just gonna rewrite the problem here. I think that's easier to look at. Okay. I can use my properties of exponents to say that this is 2 to the 2 plus x power, can't I? So, they're the same. That's equal to h of x. We got to see what is going to happen when we graph f of x equals 2 to the x power, and let's not graph h of x and g of x. They're the same. That would be weird. So let's go ahead and just graph h of x. Two to the x power. Actually, let's go ahead and make a table of values here. So we'll have x, f of x, and g of x. So let's go with -2, -1. And I'm just picking values, right? I'm just picking some x values to plug in, right? I get to choose whatever I want. These are probably going to be the easiest and the ones that'll fit on my graph, hopefully, right? So f of x is 2 to the x power. 2 to the -2 power is the same thing as 1/4, right? 2 to the -1 power is the same thing as 1/2. 2 to the 0 power, 1. 2 to the first power is 2. 2 squared is 4. 2 to the third power is 8. Let's go ahead and graph those. So we're at 2, 1/4, somewhere around there. 1, 1/2, somewhere around there. At 0, we're at 1. At 1, we're at 2. At 2, we're at 4. And at 3, we're at 8. So here we go. Look. We're able to do it. What do you think is going to happen for extremely negative values of x? It's going to get super, super close to 0, but it's never going to touch because apparently it has been friend zoned. Yeah, technically it's an asymptote, right? So this thing has what's called a horizontal asymptote at the line. Whoops. Y equals 0. Okay, let's look at g of x. What's going to happen for g of x? Okay, and I'm plugging values in here since g of x and h of x are the same. So g of -2 is going to give me 2 to the 0 power, or 1. G of -1 is going to give me 2 to the first power, or 2. G of 0 is going to give me 2 to the second power, because 2 plus 0 is 2. So that's going to be 4. Interesting pattern that's forming. Right? Don't we just have the same pattern, just offset? Offset. Oh. 18, 16, 32, right? Whew, okay, let's plug those bad boys in there. At -2, we are at 1. At -1, we are at 2. at 0. We're at 4. At 1. We are at 8. At 2. 16. And then the last point won't fit on our graph. And we imagine that this is going to have the same behavior for very negative values of x. It's going to approach the line y equals 0 asymptotically. And there we go. So what was that transformation? Yes. Was it? Yeah. No. Hold on. Sorry, my brain just took a party. Yeah, sorry, it is a, it's a horizontal shift, right? Sorry.
You got a brain in yourself.
Oh my god.
You didn't tell the brain in yourself.
And it's actually a translation of -2 units, right? Even though it's a positive x, right? We're adding, or a positive 2 that we're adding to the x. It turns out that that moves it, it shifts it in the negative direction. All right. Let's look at these exponential functions. First of all, it looks like something is up with h of x. Isn't that the same thing as 2 to the -1 power to the x power? Which is the same as 2 to the -x. So hey, it looks like they tricked us again. Yeah, and tricks are for kids. Wait. So then they're for you. Alright, here we go. You know what? Let's go ahead and go to our handy-dandy graphing calculators and graph these and see what happens. So we're going to graph 2 to the x power. And we're going to graph 2 to the -x power. Dang it. What? Come on, Elliot, be good. Ooh. What happened? When we made x negative,
Just cuss out the song.
that's the technical master. No, we made a reflection about the y-axis, or better described as the line x equals 0. So let's make a rough sketch of that. He said it was looking. I switched to crayon? That's crazy. Okay, we're here. Something like that. That. You know, okay. And since it's a reflection, we saw that with our, and more specifically, it's a reflection about the line x equals 0. We can graph this just by reflecting the points. Right? If I have a point here, it's going to become here. This point. Whoa, I did it wrong. That. There we go. We'll go ahead and graph these. And then over here. Well, not a very good graph, but here we go. We have g of x over here, and f of x over here. All right, let's go down here and talk about the transformations of logarithmic functions. What's going on? We talked about what was happening with everything except for one of those. This coefficient of 2 we didn't talk about, right? But we did talk about this. What is this? This is a vertical translation. What did this one do? It was horizontal, and in particular, this one was positive 3, right? And even though it's a negative 2, it doesn't move it in the negative direction, right? It's going to go plus 2. And we're going to call this scaling. That one is going to scale it. So we're going to graph the common logarithm, f of x, and g of x on the same axes, but I'm going to go ahead and make a table for g of x, okay? And remember, since it's on the other page, g of x was 3 plus 2 log base 2 of x minus 2. Alright. So, for... Was it base 2, guys? No, it was base 10. Well, it's going to affect the points I want to put there, okay? Yes, because g of x is 3 plus 2 log base 10, not log base 2 of x minus 2. All right. So, let's go ahead and use our handy dandy graphing calculator. Actually, let's get these. So I'm trying to pick values that are going to give me nice whole number values, but log base 10 is really weird because it only works really nicely for powers of 10, right? So it's going to look a little weird on this graph. Let's go ahead and use our graphing calculator. Plus, I have a log base 10 button, so it's pretty convenient. So let's look at log base 10 of x. And let's look at 3 plus 2 log base 10 of x minus 2. They technically do. This one technically has an asymptote. Here at x equals 2. So it's actually That's actually it. And you could just draw a rough sketch of those, okay? Just draw a rough sketch. You know, alright, so let's go back. There is some. Alright, so general transformations of exponential functions. What's going to happen? This little 2 here is going to be a scaling. I'm sorry? Lies. I lied to you. The power is what gives me our scaling, okay? This 2 right here is going to wind up being a, well, let's look at it. It's going to wind up being a horizontal translation because I could rewrite this as I'm not sure that was helping. Sorry, that's not helpful. There we go. This is a vertical translation. And then we'll also have some scaling for this. It's true. All right. Try G as a transformation. Okay. So 9x is the same thing as 3 squared to the x power, which is 3 to the 2x. So it's going to scale it. It's going to cause it to increase more quickly, yes? And this is going to be kind of like our parent function, right? All right, so let's go ahead and use our calculator to graph each of these. So we'll graph 3 to the x power. We'll graph 3 to the 2x power. And we will graph 3 to the 2x. There's a parent function. There's a horizontal scaling, and then a horizontal scaling, and a horizontal translation. All right. Go ahead and sketch that in the area there in your book. And let's talk about looking at these different transformations. Alright, so here we're going to have scaling, and this is going to be a horizontal. This right here, it turns out, is actually a vertical translation.
Whoa. Strong for two.
And why is that? Because you can break it up. G of x is also log base 10 of 100 plus log base 10 of x. This negative is a reflection. About y equals 0, or the x-axis. Here we have some scaling. And that is a horizontal translation. And what that is actually going to be a horizontal translation. So here we have our reflection. And actually, let's take a look at the graph of this one. It's going to be very interesting. It's going to be horizontal. Let's look at this in our graphing calculator. Go ahead and do that on your own. I gotta cut this video short.